Good morning. A lot of segments in this section. So bonding is one of our longest chapters. I hope you're bearing with this. This is segment 5 of compounds and their bonds. And so we were talking about ionic compounds, ionic naming, then we started talking about molecular naming, and now we're going to talk about how to form molecules. So how are molecules formed? Well, we're going to be looking at covalent bonding. So here we will not have charges. We won't have ions. And we're going to look at something like hydrogen. Hydrogen is a diatomic molecule. We'll see that in another couple segments coming up when we'll talk about diatomics. But we're going to use that as our example now. And if I think about hydrogen as a gas and the two hydrogens and what's going on there, remember that the protons themselves, because a hydrogen is simply one proton and one electron. And so if I start to bring those two protons near each other, they should repel, right? Two positive charges should repel each other. All right, so if the nuclei repel, what could possibly going on then that would form a bond with H2? And of course, what else is there? Well, there are the electrons. So while the two nuclei would repel each other, the two protons would want to get as far away from each other as they could, they do want to collect those electrons, right? So they are attracted to the electrons. So instead of thinking of it as just two protons sitting there, I'm going to rearrange our structure. So now we have the two protons here and here, but now the electron that's in that cloud, we're going to kind of bring near each other. Now the electrons are also going to repel. So they're going to want to get as far away from each other as they can, but the protons are attracted to both. And remember, all of these atoms want to have noble gas-like structures. Do we have a noble gas that has two electrons in its outermost shell? And I think the answer to that is yes, right? Helium. All right. So once they can start sharing these electrons, then they can start to count them towards each other. So now each hydrogen, we get to count both of those electrons since they're being shared. Now, by sharing them, they will get to count both. So both electrons would count for each hydrogen. Whenever we share electrons, we call that a covalent bond. So this is going to be for nonmetals. Nonmetals are going to hold on to their valence electrons, right? They typically have 4 or more electrons in their outermost energy level. And so they don't want to let those go. They're not going to give away any of their electrons. But again, the game is still the same. We're trying to fit the octet rule. We want to have 8 valence electrons so that we can have a noble gas configuration. Except now, instead of losing electrons, we're going to have to share them. So the key word is going to be share. We're going to be sharing our valence electrons. Now, when we share electrons, both atoms get to count those electrons towards their individual configurations, right? In essence, that is a covalent bond. So let's look at a second example here. Let's take fluorine. Fluorine has several valence electrons. In fact, it has 7, right? Almost full. And so there's our electron dot structure. We have the fluorine, 7 valence electrons, 3 lone pairs, 1 individual electron. And fluorine, much like hydrogen, is also going to be diatomic. And so we're going to have a second atom of fluorine also with 7 electrons. Now I've arranged these dots so that you can see the linkage here, right? We can see how these two are going to fit together. So even though the protons may repel, and a lot of the electrons are going to repel, those pairs of electrons want to form a covalent bond. Now, here I've made the bond, so it's connected. Now let's count electrons. Okay, so by sharing, remember each fluorine gets to end up with a full orbital. So if I look at this fluorine first, I can count electrons. 1, 2, 3, 4, 5, 6, 7, 8. And now when I go to count the second fluorine, remember the two in the middle are like a fence in between the two neighbors. And both neighbors get to count the electrons that are making up that fence. And so the second fluorine also gets to count 1, 2, 3, 4, 5, 6, and 7, and 8. So both of these fluorines then are going to be happy, right? Because they've completed their octet. Now, whenever we share a pair of electrons, so we're sharing 2 electrons, we call that a single covalent bond. So 2 electrons make up a single bond. Now that's only going to be for nonmetals and hydrogen. Metals will not do this. Metals give away their electrons. They transfer them. Okay. Now, again, this is completely different from an ionic bond. Number one, remember for the ionic bonding, it was a sea of different ions, plus and minus, that are surrounding each other. Here, we're going to have two very specific atoms that are going to be joined in a very specific way. So if we have a single bond and they're sharing those two electrons, they're stuck together, right? They're sharing them, and that's it. They both get to count them. Now, in an ionic solid, we couldn't tell which atom the electrons came from or to. All we know is the electrons were transferred and the charges became a pattern where it was plus minus plus minus. Now, here you're going to have to be able to draw them out. So when we do ionic compounds, we don't typically show the transferring of electrons. I did that in the last segment just to make sure you could understand where the electrons were going to and where they were coming from. Here, you're actually going to have to be able to put them together. So how do we do it? Well, it's like a jigsaw puzzle. So number one, I'm going to have to tell you what the final formula is going to be. I'm not going to expect you to know that. So even for common compounds like water, it's still going to say water, comma, H2O. I'm going to give you the formula. Then what you're going to do is put those pieces together so that you end up with the right connectivity and that everybody fits in the octet rule. And speaking of water, we'll take a look at that one. So our example will be water. We're going to look at the covalent bonds that are used in water. So we know we're going to start with H2O. We know we have hydrogen with a single dot. Oxygen is going to have 6 dots, right? And remember, these are coming from our valence electrons, and that's coming from our group numbers. Hydrogen was in group 1, and so it has 1 electron. Oxygen was in group 6A, and so it's got 6 valence electrons. Now, each hydrogen has 1 valence electron, which means it's going to want 1 more. It's one of our exceptions, right? It only wants 2 electrons to be happy. So even though it's the octet rule, hydrogen only wants 2 electrons. Oxygen, starting with 6, means it needs to gain 2 more. Now, what we're going to do is make these valence electrons share so that everybody's going to be happy. So I'm going to start off with water, putting the pieces together. I'm going to start with 1 oxygen and 1 hydrogen. At this point, when I look at the hydrogen, it's got 2 electrons, right? Because it gets to count both of the electrons that are being shared. However, the oxygen only has 2, 4, 6, 7. Now that's okay because remember the formula is H2O. So while the first oxygen may be happy, this oxygen still wants more electrons and we still have a second hydrogen to add. Now I'm going to attach the second hydrogen. I'm going to fit it right there, and of course now it's going to share these 2 electrons with the oxygen. At this point, this hydrogen and this hydrogen are both happy with just 2. The oxygen gets to count the 2 from this hydrogen, 2 from the original hydrogen, and then it's got 4 of its own. That gives it a total of 8. All right, so now that we've attached that second hydrogen, we can see that each atom has a full energy level, right? The hydrogens have filled the first energy level. That meets the requirements of the octet rule. The oxygen also gaining 2 electrons has met the second energy level. So they're both going to be happy. Now, there are cases when we're going to have to make multiple bonds. So the atoms are able to share more than 1 electron. Okay, so sometimes atoms will share more than 1 pair. If they share 2 electrons, so each atom is sharing 2 electrons, that's 4 electrons total, we call that a double bond. If 2 atoms share 3 electrons each, that gives us a total of 6 electrons being shared, and that means we have a triple bond. Now you'll be able to distinguish this because all 4 of these electrons and all 6 of the electrons in the triple bond will be in between the 2 atoms that are sharing. So let's take a look at an example. Here's carbon dioxide. Now, carbon dioxide is CO2. And here I'm even going to tell you that carbon is in the middle because you could make the dots work out as COO, putting a carbon on the end and putting oxygen in the middle. With water, I didn't tell you that because oxygen had to be in the middle. The hydrogens can't have more than a single bond. Remember, they only have 1 valence electron, so they can only make 1 covalent bond. Here, carbon or oxygen could be in the middle, so I tell you that carbon is the central atom. So that means everything's going to connect to the carbon. We know that carbon has 4 valence electrons, That means it's going to want 4 more. We know oxygen, still the same oxygen, it has 6 valence electrons. It's going to want 2 more. So we're going to attach them together like we did with the water. I'll put the carbon with the oxygen. I form a single bond, and I start counting it up. Oxygen has 2, 4, 6, 7 electrons. Not happy yet. Carbon has 2, 3, 4, 5 electrons. Also not happy yet, but I still have another oxygen. So let's go ahead and attach that second oxygen. See how this works. We have 2, 4, 6, 7 electrons for oxygen. Still not happy. So neither oxygen is happy. Carbon has 2, 4, 5, 6. Also not happy. So no one is happy yet. All right, the only solution we have in this situation then is to start sharing more electrons. So I'm going to scoot an oxygen back, I'm going to make some space, and I'm going to throw one more electron from each into the middle. Now, whatever's in the middle, whatever's making our fence, can't get the mouse here to show up. There it goes. Whatever's in the middle here is being shared by both elements. Okay, so the oxygen here gets to count all 4 of these electrons in the middle. So it's got 4, 5, 6, 7, 8. This oxygen is now happy. It has met the requirement of the octet rule. The carbon also gets to count these 4, just like it did with the pair over here. That's 6, and there's 7. So not quite happy yet. But we can do the same trick over here. I'll move that oxygen back and throw a few more in here. So now we've got 4 in this one as well. The carbon now gets to count these 4 as well as these 4. Oxygen, we'll call this one the second oxygen, has these 4 plus 4 of its own. So now both of them have 8. So it's going to require 2 double bonds. Now, that's okay. There's nothing wrong with that as long as we meet the 8 valence electron requirement. So carbon has 8 valence electrons here, oxygen has 8 there, and the second oxygen has 8 there. Now that's fine and dandy because Mr. Caro was the one that helped you out with that one. How would you have gotten that by yourself? And that's where it becomes a little more difficult. So what we're going to do is figure out a method that will work for all of these compounds. And so what we're going to do is look at how we can draw these out. So what we want to do first is take a list of atoms and add up all the valence electrons that are in the formula. So if I were to go backwards and look at CO2, I would take 4 for the carbon, 6 for each oxygen, right? So that would give me a total of 16 valence electrons. Then I'm going to figure out how many I need to make everybody happy. Now don't worry about the valence electrons anymore, just what does each element need? So hydrogen's going to need 2, and everybody else is going to need 8. So I had 1 carbon and 2 oxygens, each wanting 8. So that's 3 atoms that want 8 electrons for 24. Now I'm going to subtract those 2. So I need 24 to make everybody happy. I have 16. So 24 minus 16 gives me 8. Now I want to divide that by 2. And the reason why I'm going to divide that by 2 is there are 2 electrons in each bond. So I had a difference of 8 electrons. I divide that by 2, that's 4. And what that number is telling us now is how many bonds we need to draw. And so we can draw the bonds in first and then add lone pairs of electrons to make things fit. All right, let's give it a try. So we're going to do NH3. Now realistically, if this was an assessment, I wouldn't expect you to use these rules to figure out all the bonding here. You could simply do it just like we did water, put nitrogen in the middle, connect the hydrogens, and be done. But I just want to walk through it nice and slow just to see how all these numbers are going to work out for us. So nitrogen has 5 valence electrons, but it wants 8. Hydrogen has 1 valence electron, but it wants 2. Now keep in mind though, we have 3 hydrogens based on the formula. So the halves, ammonia, NH3, has 5 electrons coming from nitrogen, 1 electron coming from hydrogen, but we have 3 of it. So we're going to do 3 times 1. So 5 plus 3 times 1 gives me 8. I have 8 valence electrons. For the wants, I have nitrogen wants 8, hydrogen wants 2, but again, I have to account for all 3 hydrogens. So 3 times 2 is 6, plus 8 gives me 14. Now we'll follow this little pattern. 14 minus 8 gives me 6. 6 divided by 2 equals 3. So that means NH3 as a formula should have 3 bonds. Now what I'm going to do is just draw those in. So I'm going to go, okay, here's the nitrogen. I know I need 3 bonds to 3 hydrogens. So there they are. Now I can count electrons. Hydrogen 1, 2 electrons is happy. Hydrogen 2 on top here, 2 electrons, it's happy. Hydrogen 3 to the right, 2 electrons, it's happy. Nitrogen, 2, 4, 6 electrons, not quite happy yet. In order to make it happy, I need to add 2 electrons. So I'm simply going to draw them in. Now nitrogen has its 8 electrons. It should be happy. But what I want to do is make sure I didn't cheat here. How many electrons were we allowed to have? So if I go back to the previous slide, we'll see that we had 8 electrons as a have. And that's how many electrons we've got, which means we've probably done this correctly. Everything is full. Everything has met the requirements of bonding, and we only use the electrons that we have. Once you finish all 3 of those check marks, then you've probably got the right structure. All right, let's do another example. Step it up a notch a little bit here. We're going to do HCN, and I'm going to tell you that carbon is central. So we know that carbon is in the middle. The nitrogen and the hydrogen are both connected to the carbon. Now I'm going to give you a second here to pause. So you can pause this video and try to work this problem on your own using the rules we just used, or maybe even rewind a little bit. Okay, so now you've pushed play and you're ready to see how we're going to do this. So nitrogen has 5 valence electrons, but it wants 8. Carbon has 4 valence electrons, but it also wants 8. Hydrogen has 1 valence electron, but it only wants 2. So for my halves, I know that hydrogen has 1, carbon has 4, nitrogen has 5. 5 plus 4 plus 1 gives me 10. For once, nitrogen wants 8, carbon wants 8, hydrogen wants 2. That's a total of 18. So now remember, the math here is going to take my wants minus my halves and divide by 2. So 18 minus 10 is 8 divided by 2 equals 4. So this compound is going to have 4 bonds. Now another point though is we're going to need multiple bonds, but we're not going to be able to make multiple bonds to hydrogen. Okay, so we're not going to be able to make multiple bonds to hydrogen. So the first thing I'm going to do is put in my single bonds. So there we go. We know that carbon is central, so I got carbon in the middle. I've got a single bond to the hydrogen. I've got a single bond to the nitrogen. That accounts for 2 of our bonds and 4 of our electrons. Now, at this point, hydrogen's happy. Carbon, not happy. Nitrogen, not happy. So now I'm going to need 2 more bonds. Our calculation said we needed 4 bonds. I'm going to put those 2 bonds in between the carbon and the nitrogen. So I'm going to move that nitrogen out, and I'm going to stash some more electrons in there. Now the maximum we can have is a triple bond. Now this course, we're not going to worry too much about why, but you're just going to have to trust me at this point. You can't have anything greater than a triple bond, so we've maxed out. We do have all 4 bonds though, which is what the math suggests we should have. At this point, the hydrogen we know was already happy. Making a multiple bond over here doesn't affect the hydrogen. The carbon now has 2, 4, 6, 8. It's happy. The nitrogen gets to count all 6 in the center, but it's missing 2. So just like before, I'm going to go ahead and add those 2 electrons on the nitrogen to fill the orbital for the nitrogen. Now the nitrogen's happy. All right, hopefully that made sense. Again, we still have to do check marks if we want. We've used 4 bonds, just like our calculation suggested. We've made sure that everybody is happy. Check mark there. And of course, we haven't done anything crazy like give hydrogen a bunch of extra bonds. Okay, that means we've probably got the structure correct. Now, there's another way to indicate bonds, and the other way is to just simply use a line for a bond. When we do that, it's no longer a dot structure. It's a structural formula. So the semantics change a little bit, the look will change a little bit, but basically what we're going to do is start with water this way and say, you know what, it's a little harder to understand what's going on there. I can get rid of some of those dots by simply drawing in lines for bonds. Now notice the lone pairs were left as pairs. That becomes important in later chemistry courses, not so much this one. But some people will actually put lines for every pair of electrons, and I don't want you to do that. That's a bad habit to get into. I want you to have open dot lone pairs. Again, most of you are probably not going to go on in chemistry, right? You're taking this course for nursing or paramedic, and you just need to get this chemistry course out of your way. I get that. But for those of you that do move on and do want to go on or end up going on, even though you didn't know it was coming, if you have to look at organic chemistry, those lone pairs are going to be significant, and you're going to want to be able to use those to figure out structures and bonding and some other things that might be going on. And so I want you to practice good habits, which means I want you drawing lone pairs. So feel free to use the lines when you're making bonds, but they need to be lone pairs if it's not a bond. Now, some of the structures we've just worked on, there's that HCN, but now you can see it's a lot easier to see without all those dots. We have a single bond and then a triple bond. You can also see why it's called a triple bond versus a 6 bond or something along those lines. And again, we've left that lone pair open. Now, no matter how I add it up, I should still come up with carbon having 8 electrons, right? I should still have nitrogen having 8 electrons, and I should still have the hydrogen with 2. And here's a second structure that we didn't work on, but you should be able to do the same things here. The carbon we can see has 8 because it's 4 pairs, 4 bonds is 8 electrons. Oxygen has 2 lone pairs, and of course the double bond in the middle, so it's sharing 4 electrons there. Now we've just looked at 2 different types of compounds, and I'm going to wrap up with this, and then we're going to change gears to electronegativity. When you're looking at these 2 types of compounds, the smallest piece for an ionic compound is going to be a formula unit. For the molecular compound, we refer to it as a molecule. So these things are definitely 2 different items, okay? They are both substances, right? Because they are compounds, they are connected, but one is a formula unit, one is a molecule. We see this in the types of elements. For ionic compounds, it's going to be a metal and a nonmetal. And for the molecular compound, it's going to be mainly nonmetals, if not all nonmetals. For us, it's all nonmetals. But when you get to advanced chemistries, you can get into some organometallics. For the state, ionic compounds are almost always a solid state. They're salts, so they're typically going to be solids, high melting points. On the other hand, molecular compounds vary. We can have a solid, a liquid, or a gas, so we can run the whole range. Solids would be stuff like sugars, right? They're solids. Liquids, you can look at fuel oils and gasolines, things like that, or even water if you want to get real technical. Then there's gases, CO2, water again is a water vapor, humidity, nitrogen, oxygen. These are all molecular and they're gases. And again, we can tell usually with melting points. By rule of thumb, no guarantees here, melting points for ionic compounds are typically well over 300 degrees Celsius. Whereas for molecular compounds, they might be a little lower. So they'll be under 300 degrees Celsius. And again, that's a rule of thumb. That's not a guarantee. All right, so that's going to end segment 5. We're going to pick up in segment 6 with electronegativity. So now we're going to talk about the differences in these bonds. So not only do we see physical states and physical properties for the 2 types of bonds, we're going to see something else, which is electronegativity. All right, so stay tuned, and I think we'll be finishing up this chapter in the next segment.